So welcome everybody. So this is the second section of the 6 seminars on random geometry and quantum gravity. This is the theme we are working on in this trimester. So and today we are very happy to have William da Silva from Vienna, who is telling us about the scaling limit of the volume of the loop point quantum quadrangulations.
Yes, thank you. Thanks for the invitation. So I'm going to report about a joint work with Élie, Aïdékon, who's in Fudan University, and XingJian, who is a PhD student, and who is actually in the audience. So it's a nice opportunity for me to advertise that he's going to be visiting Nicolas' group per year. Want to chat about planar maps, he'll be around. Okay, so the model that we're going to describe is it's called the LUPON model, planar map model, and so it's a model that comes from theoretical physics, and this particular model is the interest of this particular model is that it is related to different universality classes than the usual Brownian geometry. So I'm not sure what the background of the audience in general is. I'm going to start by describing the general properties of the model. So this is all going to be very basic. So as I said, it's a model of planar maps which are decorated with loops living on the faces of these maps. So I need to define these maps and the loops. So the planar map that we're going to consider again, I'm not sure I need to introduce these objects to this particular audience. So I'm going to think of them as a gluing of polygons living on the sphere. So they're planar graphs like this. And yeah, I'm not going to look at the shape of the edges. All right, so this is the same planar map. But this is different from this map where you've put the edge inside this component. Okay, and all the planar maps that I'm going to consider are going to be rooted. So this means that I'll have a special oriented edge that comes with this object, with the planar map. Call it E, and with this edge, I can define the notion of external face or root face, which is the face to the right of this edge. So remember that we're on the sphere, so this is a well-defined face on the sphere. It's living outside this drawing now. So this is the root, and this is the root face or external face. Yeah, also feel free to interrupt and ask questions if you want. An important parameter for us is the so-called perimeter of the map, which is just the degree of the external face. And by degree, I mean the number of edges you find in your face when you're drawing the contour of that face. So in this drawing, the perimeter is 5, because so you find this when you draw the contour of this face, you find this edge twice, this edge twice, and this one once. So you have 5 edges along the face. Okay. And so I'm going to look at a specific model map, which is that of quadrangulations. So we're going to stick to quadrangulations from now on, where all the internal faces they have degree 4, meaning that you essentially have two types of faces, either squares like this, or something like this, which also has degree 4. Okay. So the general question for this talk is, what can we say about the volume, the number of vertices of these maps when you're fixing the perimeter, degree of this external face, and sending it to infinity? So I need to introduce the loops in the model as well. So these are just a collection of loops that are crossing the faces of the quadrangulation. They are disjoint and possibly nested. And they have the important restriction or condition. It's called the rigidity condition, which is that I'm forcing loops to cross squares through opposite edges. Okay, so I'm forbidding situations where I have a square like this, and the loop is taking a turn in the. Okay, so I'm just going to look at loops like and quadrangulations that are like this, where the loops are crossing through opposite edges. Okay. So another way to say this is that a loop is just a necklace, a gluing of these types of squares that are crossed in this opposite edges way. And this is going to give me a sample space. So it's going to give me a set of quadrangulations with fixed perimeter. Call it 2B, because it's always even, because we're looking at quadrangulations. With a collection of rigid loops on top. It is by sort of sample space, and all of this was deterministic so far. And now we need to introduce the right measure that we're going to look at if we want to do probability. So this is the loop ON model. And for this, I need 3 parameters. So I have G and H, which are positive, and N, which is between 0 and 2. And I can define the weight of a loop decorated quadrangulations. Here is the quadrangulations, and this is the set of loop. It's a collection of loops. And the weight of this is just going to be G to the number of empty faces times H to the number of faces that are crossed by a loop. And N to the number of loops, the cardinality of this set L. This is the Lupo-N model. I mean, this is a Lupo-N weight. And if I want to introduce a probability measure on OP, what I want to do is to introduce the partition function FP, which is defined as the sum of these weights over the set OP. The annoying thing is that this thing could be infinite. So if you want to introduce the probability measure by renormalizing the weights, you have to assume that FP is finite. So basically, whenever FP is finite, you can define a probability measure, which I'm going to call P, N, P, H. So it depends on all these weights. And then P, and this is just the weights renormalized by FP. So this is a measure that is sampling a loop decorated quadrangulation that lives in OP. Should I use the blackboard inside or? Yeah. Okay. So the first important thing to look at is whether this partition function is finite or infinite. Right, if we want to define a probability measure. And so there's a work of Borot that classifies the behavior of this partition function according to the regions of G, H, and N that you're looking at. So here I'm going to fix N to be in 0, 2 excluded, and including this. Oops. Yeah. Okay. Excluding this this value 2 from this previous model for the moment. And what they managed to prove is that the phase diagram looks the same for all fixed value of N in the GH plane. And so the first information that they can say is that there's a critical line, critical curve, above which FP is infinite in the whole region above this line. And then below this line and including this line, the partition function is finite, and so we can define a probability measure. And then more importantly, what they managed to prove is that they have this classification of the regions of parameters depending on the behavior of the asymptotic behavior of this FP. So in all cases, FP is going to be like a constant times some geometric growth, and then going to get P to the alpha plus a half. This is just a convention. It's P to some exponent I'm calling alpha plus a half. And depending on the region that you're looking at, this exponent will be different. So first, in the whole region below this line, alpha is 1. On this curve, there's a portion, this white portion where alpha is equal to 2 all the way. And then there is there's another region here, corresponding to that side of the curve, plus a special point where the exponent is different. And it has the very nice formula, which is given by 3/2, and then there's a plus or minus depending on which part of this region you're looking at. That is 1/5 r cos n/2. So it's related to n. It's kind of uniform over the whole blue line, and changes when reaching this blue point. So there's a bit of terminology around this phase diagram. We call this red point dilute, and this blue phase dense. And the general thing, including blue and red, is called critical non-generic loop and model. So I'm going to restrict to this this region from now on, because this is the region where where you're expecting to escape from the realm of Brownian geometry. This is the main region of interest of this Silva model. The way they prove this is using a technique that is very powerful, that is called the cascade decomposition. I'm not going to expand on that. But so let me say that this was for n strictly less than 2. But for n equals 2, with XingJian and Élie, we managed to extend this phase diagram just by taking limits. And we can replace the behaviors in the dense and dilute case by, so if we take limits in both directions, get that FP is a constant times lambda to the p squared, or just p squared. So there's also a sort of dichotomy in the n=2 case, which is given by an extra log factor corresponding to this dense case. I don't really wanted to call it dense because in the limits we're expecting the loops to behave in a similar way. And I'll also say that there's a work of Emmanuel Campa, which also does this for n=2, but in more generality than what we do. So it's for dipartite maps in general. Okay, so that's the first basic properties of the model. The questions on this part of the model. So if not, so I'm going to describe what we say about the volume of these maps. So as I said, I'm going to restrict to the critical non-generic case where I have this special exponent alpha giving the behavior of the partition function. And I'll define the volume of the plane map as the number of vertices of this quadrangulation. And so the question is, if you start from fixed perimeter P, as we define this probability measure, what can we say about the behavior of this volume, which will depend on P, as P goes to infinity? Is it going to grow like in the Euclidean setting where you have this P squared scaling, or do you see other fractal exponents according to the regime in your phase diagram? So there was a first answer that was provided by Timothy Bugs. And it's answering the following question. If I don't ask about the actual volume, but more like the behavior of the mean volume, so the expected volume. So I'm going to define V bar of P to be the expected volume under this measure, which depends again on these parameters. And we're starting from fixed perimeter P. Then this behaves as a constant times P to the some power, depending on this alpha, which is given by the minimum between 2 and 2 alpha minus 1. Okay, so it's in simple relation with this exponent alpha. And a remark I want to make is this exponent separates between dilute and dense. Because if you plug in this formula, what it tells you is that the alpha is equal to 2 in the dilute case, and 2 alpha minus 1 in the dense case. Okay, so yes, I forgot to mention that this was only for n strictly less than 3. And so it's separated into the two regimes in the sense that the exponent is different in the two regimes. So in the dilute case, you get this Euclidean scaling, and in the dense case, you get something which is an intermediate exponent. And for n equals 2, we established with XingJian and Élie that V bar P is some constant again times times P squared for you see this log P correction coming from the other type of behavior of the partition function. So depending on the region above, you see different types of behaviors for the mean volume. Okay, this was the results of the expected volume. And now we're interested in what can we say about the actual volume itself. So this is our main result. And it says that, so first, if you look at n between 0 and 2, quickly, then the volume divided by 16 converges in distribution to some random variable. which by the way is explicit. And let me call this I into I. And when n is equal to 2, what we can say is that you can look at this this quantity, the same quantity as above, but now you have to multiply it by a log correction so that it converges to XingJian clearly. Also key. Okay, so this case is kind of critical in the sense that you have to add a logarithmic correction to the mean behavior to see what to get a convergence in distribution to the volume. And my plan is to try to explain where this logarithmic correction comes from in particular. And so at this point, I want to emphasize that this log is different from this log correction. As this log is holds for any of these two regimes. So it's an extra log correction that is really intrinsic to this loop O2 model. Okay. And this was so okay. These were conjectures in plane maps. So I was conjectured by the work of Chen, Curien and Maillard. And 2I was conjectured by myself and Élie during my PhD in a less explicit form. So this theorem is answering these conjectures. Okay, so I'll try and spend a bit of time describing maybe not proof itself. I want to try and convince you that this result, the nature of this result is just branching processes, which is not clear from what I said. So in order to say anything about this, I need to describe this work of Chen, Curien and Maillard, which is the reason why they came up with this conjecture. A way to see a branching process in this map is as follows. So I have my planar map with fixed perimeter 2p, and inside I have a bunch of loops. Maybe I draw the red ones, the outermost loops in red, and then inside those you have other loops. Maybe something like this. So the idea is that you can define generations of loops just by these colors, by the nesting level of each loop. And so you can code the whole thing as a tree, starting from so I have to start somewhere. So let me start from some imaginary loop outside this drawing. This loop, I'm going to call it empty. And so I'm starting from this this massive loop, blue, and then I'm exploring the planar map by generations. So I see these red loops. Then inside each of them, I can see like children of these loops. So maybe I see something like this. And I have a notion of tree given by this this notion of genealogy of the nesting levels of the loops. I actually have more than just a tree. I have a marked tree because for each loop I have a quantity that is chi p. I'm going to call chi p of u for a node u, which is going to be the perimeter, so say the half perimeter of this loop. So for the imaginary loop, since I'm starting from a half perimeter p, this is going to be just p, and then yeah, this is just the half perimeter of that loop. Okay, so what they did is essentially try to see what this looks like in the scaling limits when you take the perimeter to go to infinity, what this branching structure looks like. And so one of the results that they get is if you look at this collection for all nodes in your tree, and you divide by 1 over p, the perimeter, the half perimeter, this converges to some limiting object z alpha, which is related to this exponent alpha. And this limiting object is has a very nice description. So essentially, you can write it as the exponential of some branching random walk, whose offspring distribution depends on this parameter alpha. It's related to some alpha stable Levy process. And what this is telling you is that so in the limit, let's say in the continuum, what you see is a random walk around any point in your limiting space. Whereas in the discrete, by some spatial Markov property, what you see is a Markov chain around any vertex. So if I'm sitting somewhere on my plane map, I'm looking at all the loops that are surrounding me. What I see is a Markov chain. And in the limit, if I do the same, I'm going to observe this random walk with some specific distribution. And somehow to understand how the volume behaves, you need to understand how this branching random walk behaves. I'm going to try and give you a fake proof of our result, which was basically the idea that Chen, Curien and Maillard used to come up with the conjecture. So the heuristics of the proof are the following. So you're taking the volume, you need to renormalize it by its expectation, which in the n less than 2 cases, so something like this, by Bud's theorem. And what I'm going to do is to say, well, I can split this over the loops in my domain, and I could pick some generation in my tree, and say that I can split the volume into whatever is inside loops at generation L. Okay, so this is roughly so this normalizing factor times the volume inside. This is the volume inside the loop generation, the loop corresponding to the node U, the generation L. And here I'm saying that I can neglect everything that comes from loops from outside these loops, generation L. Right. Because what this means is that so not being in a loop of generation L, L is fixed. It's fixed but large at this point. Not being in a loop at generation L means that if you look at this branching random walk, or this loop cascade, what you see is something like this, where like you see some individuals and maybe some of them die out. And what you're saying is that at generation L, you have a sudden drop with one particle. They all start at P, and you have a sudden drop to 0 before generation L. And you can prove that this is unlikely. So given this, you can say, assume that we knew some kind of law of large number concentration for these sums of volumes. Then you'd be able to argue that this is, roughly speaking, the same sum, but now taking the expected volume started from this half perimeter, which is given by the size of the loop. Okay, so now inside loop U, what you see is a copy of the loop 1 model, but with half perimeter given by this value. If you assume this and then use the asymptotics for the mean volume, then what you see is that this is it's going to be lambda times u to the theta alpha over p. Okay. So this is just the P large. The P large, we know that this thing behaves like P roughly from this result. So this is going to infinity. And we can use the asymptotics for the volume to say that this is roughly this sum. Now I'm going to use this again to say that, well, as P is large again, this is roughly this sum, replacing the discrete cascade by this limiting branching on the mode type of object. And this happens to be a martingale. So it's a very classical factoring like branching on the mode theory, which just converges to something which is the limit of some appropriate additive martingale. Okay, so it seems that everything is proven but for this concentration argument in the n less than 2 cases, strictly less than 2 cases at least. But if you want to prove concentration, this is actually the hard part of the claim, and I want to try and spend a bit of time to try and see why this fails. Well, a few comments about this. So if you want to prove concentration in general, you'd like to have a second moment estimates to the volume. And it turns out that in our case, the second volume goes up. This is definitely going to fail. And similarly, if you look at say, characteristic functions, it's not so clear from the expression that you get how to handle these things. And this is basically why Timothy Butt came up with these random walk techniques to derive its mean asymptotic results. So in order to prove concentration or some kind of concentration, we need to understand the behavior of loops. Just to use this approximation. And so our strategy is to use a sort of second moment method, but truncated in volume into a good region and a bad region, where this we can rule out using first moments. These would correspond to loops which are atypical in the system. And we have the remaining portion of the volume which corresponds to typical loops, where we have good control through second moment. So this is the square integrable portion of the plane map once we remove this. But coming up with a classification of good and bad loops is the tricky part of the loop. Like, it's not clear at all from what I said. Okay, so that was the first comment. Second comment is that the n equals 2. The heuristics failed. Because you expect, from the result I stated, you have this extra logarithmic fraction. So this thing should go to 0. And indeed, in this case, the only thing that it tells you is that since W infinity is 0, almost surely, from branching on the walk argument, what you see is just that if you divide the volume by p squared, then this converges to 0. It doesn't give you the right scaling, so the conversion in distribution. And as is usual in the case of branching on the walk, you need to introduce the so-called derivative Martin. So this critical case is actually way more difficult than the regime where n is strictly less than 2. And finally, do you have like 10 minutes left, or it's 5 minutes? Or... Yeah. Yeah. So I'll spend a bit of time to try and explain where this log comes from in our statement. Log statement. So as I said, if you want to come up with a classification of the map of the loops into good or bad, you need to understand what is the full behavior of a loop you chosen at random in your playing map in some sense. So what you can do is you're going to choose a vertex at random in your plane map uniformly, and see what the cascade of loops looks like seen from that vertex. So what we want to do is to introduce this tagged loop, or tagged branch, or let's say particle if we're taking the point of view of branching on walk, whose distribution is given by the following. So at each step, the distribution is given by a sum of all the loops at this first generation of f of so I'm looking at let's call it a star. I'm looking at this special process whose law is given by you. So what this is telling you is that you're picking a loop proportionally to its volume, because this is the conditional volume given the perimeter. And you look at what you observe in your cascade. So remember that here, ZR, I recall that it's e to the branch to some branching random order. And here I'm looking at this branching random order directly, so I'm taking the log of this, so that if I look at, say, S star n, which is the sum of IID copies of, so a random walk given with this step distribution, and Z star of n, which is given by e to this sum, is what we're going to call a typical, describing the behavior of a typical loop, and this is the so-called tagged particle. Tagged particle. Okay, so in other words, what we're doing is that we're looking at the planar map, and at each step we're targeting, we're picking a loop at random proportionally to its volume, and see what the behavior of the cascade looks like from this point. Okay, and this is all from the continuum side of things. So you can do the same in the discrete, but this is for the limiting object that we have. And if you want to understand what the question about the behavior of a typical loop in the system or in the limit, so a typical particle in your branching random walk, you can phrase this as what's the behavior of Z star. By definition, a Z star, this is how we define it. Yeah, as a type particle. So this behavior depends on this offspring distribution xi hat, the xi star. And so it turns out that when n is between 0 and 2, the expectation that psi hat is negative. So in all this regime, you have a drift for this offspring distribution, which is going to translate into the fact that typical particles decay exponentially. Right, remember that a particle is e to this distribution. And so this will help if you want to prove a concentration argument. On the other hand, if you look at n equals 2, then you can see from the explicit offspring distribution of the branching on the walk that this thing is 0. So it's not clear what happens. And in order to say anything about this case, the usual branching on the walk argument is to use a notation to see that. Where you're going to look at a barrier for these particles, and you're going to force them to stay below some fixed value b. Then, when removing, so when you add a barrier, you have the right decay that you want. But now removing this barrier, it has a logarithmic cost. This is something that is well known from random walk and renewal functions in general. Right, and the only thing I want to mention as finally is that all of this. So importantly, all of this that I described at the end is dealing with the limiting cascade. So the main assumption is that we want to deal with the discrete model, with the plane map model. So we want to deal with Markov chains. So all of this that I described was branching on walk, which was describing this limiting object. But actually, what we want to say is something about the Markov chain, which is related to this the plane. And so this is the real hard part in the n equals 2 model, that we need to say something very precise about the speed at which this converges to its limiting branching on a walk. And for this, we use the coupling argument between the discrete and the continuum object in order to say that we can deduce the behavior from that of Z alpha. Okay, so this gives you like sort of the intuition or the reason why the log is coming, where the log is coming from. But actually, you need to deal with the discrete thing, which makes things a lot harder. Yeah, I think that's all I wanted to say. Thank you.
Any question? From even the Zoom, perhaps? Chen, that you know.
Maybe just like the last thing you said, is it a generalization of the result of BAD 2018 or something else? This when you say that you have to.
This thing?
Yes.
You mean generalization of the expected volume thing? Or?
Yeah.
Not really, I think.
So I
So-
thought there is this Z.
The thing that I erased? Or?
Yes,
Ah.
the Z alpha that goes to this exponential.
Ah, right. Yes, right. Yeah. You need some generalization of this, the n equals 2 case. So,
Okay.
Yeah. Yeah, exactly.
It's a bit.
But the coupling is right. So the coupling requires more than just this. It requires extra work, and it comes from the fact that we can have very precise control on the partition function in general.
So if there are no, yeah, please.
So, do you think you can do the same thing for the Xing model?
So I'm not sure I can do it for the easy model. Yeah, I'm not sure how to do it. I think we have to look into it.
The Daisy model is not the n equals 1 limit.
So it's the n equals 1. I mean, it's the n equals 1 case. There's a bijection between two models.
So you think, for example, the results between n equals 0 and 2 excluded do not include the n equals 1?
It includes n equals 1.
Okay.
But if I remember correctly, like the volume for the model, wait. But yeah, I can't really remember how the bijection works. But I'm afraid that you might change the.
So, but if you have a cascade decomposition,
Yeah.
And if you know the asymptotic of the partition function, I think your techniques apply.
But then, so okay, so all of this was for the rigid model. Right? So for easing, I guess you have to escape from this. Right?
Where did you use the rigidity or something?
We use it for all the behaviors for the partition functions. So at this very basic level, this is all like known for the rigid case. If you want to escape from the rigid model, and in particular in the easing case, I guess you'd have to give me what the partition function is, and then probably we can run the same argument. Like the techniques are robust in some sense, I think. But it just needs as an input some non-trivial data that comes from like, analytic combinatorics. I'm not sure we have.
Any other question? Okay, so if not, we thank our speaker again. Thank you.
Very good.